This video is going to focus on the area and volume type questions that you're going to see on the AP exam. Just a side note is that typically for the Calc BC exam, these would be polar questions usually, but this year you're not being assessed on polar functions, and so this is just going to focus on non-polar FRQs that involve area and volume. So let's start with an overview about the types of questions you're going to see with these types of FRQs. So typically the same kind of questions are asked for each of these types of FRQs, and usually you're going to have to do the following. So a common question is finding the intersection point or points of two functions. And these are typically going to be the limits of integration. Next, most of these questions you're going to have to find the area of some region. Usually it's denoted as the letter R. So find the area of a region between, there's kind of two scenarios you might see. So we're going to find the area of a region between a graph and the x-axis, or the area of a region between two graphs. And to find the area of a region between two graphs, we take the integral from one limit or point of intersection to the next, and we take the upper function and we subtract the lower function in the integrand. Okay, next, finding the volume of revolutions. I'll just say revolution. Typically, this is going to be the disk method. So often, especially if it's a no calculator question, this will just ask you to set up but do not evaluate the integral that represents the volume generated when some region is rotated around one of the axes. Finding cross sections is also a common question. So finding cross sections, either perpendicular to the x-axis or the y-axis. Especially for BC, either one of those situations is fair game. And then lastly is finding, this is only for BC, finding the perimeter using, so the perimeter of some graph using the arc length formula. So the arc length formula. Okay, so similar to the last few videos, we're going to go through two FRQs that kind of outline the common questions you're going to see associated with this concept. So FRQ number 1. So here we have a situation where we have two functions that are graphed on this coordinate plane here. And the idea is we have one function g of x, and the second function is h of x. Okay, before we do anything, let's just determine which function is which. The way we're going to approach this is to determine which function is which by using the y-intercept. So what I'm going to do for each of these functions is plug in x equals 0. Let's start with g of 0. Well, g of 0, I'll do it in blue. G of 0 is going to be the y value of the function when we plug in x equals 0 into this equation here. So if I plug in x equals 0, I get negative 2 plus 3 times cosine of 0. Cosine of 0 is the x value at 0 degrees on the unit circle, and that is a value of 1. So we end up with negative 2 plus 3, which is 1. And so this function right here is g of x, which means that h of x is going to be this function. Okay, and that's going to be important in determining which function is which when we approach problem 1. So the first question wants us to find the area R of the region in between these two functions. R is going to be equal to the integral from one value to another value, we'll talk about what that is, of the upper function minus the lower function. Okay, so in this case, the a value, the starting x value is 0, and the ending x value is given to us. It's the vertical line x equals 2. And so what we're going to do now is plug in the upper function and subtract the lower function, which is, I'll write this in parentheses, negative 2 minus 3 cosine. So negative 2 minus 3 cosine of pi over 2 times x. And then there's a dx over here. Okay, the main difficulty here is just going to be evaluating this integral. So let me actually just rewrite this real quick before we integrate it. So these two terms I'll keep the same. And I'll distribute the negative to these terms here and here. So we get plus 2 plus plus 3 cosine pi over 2x. All right, dx. So let's integrate this now. Then we're going to plug in the upper bound, subtract what we get when we plug in the lower bound. Integral of 6 is 6x minus the integral of this statement right here. You can think of it as a u substitution question, but the function inside x minus 1, the derivative of that, has a value of 1. So we can kind of just think about it as integrating the outside. So we end up with 2x minus 1 squared over 3 plus the integral of 2 is just 2x. All right, and this one's going to be the trickiest. So it looks like I messed up a sign right here. This should be a plus right here, which means that this is minus. Sorry about that. Okay, the integral of cosine is sine. So we're going to have a negative sine, but because we are integrating the composition of two functions, we're going to take out the reciprocal of the derivative of the inside. So the derivative of the inside is pi over 2. The reciprocal of that is 2 over pi. And so we're going to take out a 2 over pi and multiply it by 3. So that's 6 over pi sine of pi over 2x. You can prove that using a u substitution if you want. But if you use the u substitution, this is what you'll get for that value. All right, now let's plug in 2. So 12 minus, this becomes 2 times 1 over 3 plus 4 minus, well, if we plug in 2 here, we get sine of pi, which is 0, so this whole thing becomes 0. So that is what we get when we plug in 2. Now let's subtract what we get when we plug in 0. So 0 minus, well, this becomes, if I plug in a 0 here, I get, this should be a cube too, sorry. If I plug in a 0 here, I get negative 1 cubed, which is negative 1, times a negative in the front. So we end up getting a positive 2/3 here, plus 0, sine of 0 is 0, so minus 0. Okay, now let's simplify this. So 12 minus 2/3 plus 4, well, I'll just change this to a 16. minus 2/3, and then this negative will distribute minus another 2/3. So we end up with 16. Let's find a common denominator here. 48/3 minus 4/3 is 44/3. Okay, and that is the answer for letter A. The main difficulty in this question is just being able to evaluate the answer without the use of a calculator here, because that's the region R. Now, the second question tells us that in this region R, imagine we were to take cross-section perpendicular squares, or not necessarily squares, just a general shape. I'll write it like a square, but the shape has an area that's a function of the x, the value of x. So this area here is equal to 1/x plus 3. Okay, and the idea behind the second part of this question is that the volume generated from a cross-sectional shape, let's write it like this first, v is equal to the integral from a to b of the area. So this is a generalized form of finding cross-sections with some cross-sectional area A perpendicular to the x-axis. And so what we're going to do here is we're going to plug in, instead of writing A, I'm just going to plug in what A is defined as, which is 1/x plus 3. Now the lower limit of integration is going to be 0, and the upper limit is going to be 2. And now let's integrate this. So we end up with the natural log of the absolute value of x plus 3. You can also do u sub here, evaluated from 0 to 2. So we have the natural log of 5, absolute value of 5, but it doesn't matter because 5 is positive, minus the natural log of 3. And so you can leave your answer like that, or you can also condense this into the following. The absolute value goes away. Well, you could write it in there, but it's redundant because 5/3 is a positive number. All right, and then lastly, let's write but do not evaluate an integral expression that gives the volume of the solid generated when r is rotated around the horizontal line y equals 6. Okay, so let me kind of draw that up here so you can get a good visual, hopefully. So imagine we have the line y equals 6, which is right here. The volume, for letter C, is going to be equal to pi times the integral from 0 to 2 of the distance that is distance from the axis of rotation to the function that is farther away from the axis of rotation. So in this case, that is going to be this distance right here. Okay, and the way we're going to represent that distance is 6 minus the blue function, which is -2, plus 3 cosine of pi over 2x minus the distance from the axis of rotation to the function that is closer to the axis of rotation. That is this distance right here. So that's going to be 6 minus 6, do it in green, minus this red function here. So the red function. 6 minus 2 x minus 1 squared, close parentheses, dx. I need a second close parentheses here. Squared. Okay, so it is this distance right here, this distance, that's your first radius when using the disk method. And so it's the difference, or the distance between the axis of rotation to the function that's farther away from the axis of rotation, minus this distance, which is the distance from the axis of rotation to the function that is closer to the axis of rotation. And so this right here, sorry, it's a little messy up here. This integral statement is what you're going to write for the answer for part C. Okay, and let's wrap up the video by going through one more FRQ. Here is the mark scheme for this one. Notice the first question is the most amount of points, just because it has a lot of arithmetic they have to go through. Okay, and then to wrap up this video, let's go through the second question. Similar with the last question, the first part A of this question wants us to find the area R. So what we're going to do is we're going to do the same exact thing we did before, where we take the integral from our starting x value. So R is equal to our starting x value, 0, to our ending x value, which is the x value of the coordinate point here, which is 9. And we're going to evaluate this integral to be the upper function minus the lower function. Well, the upper function is the horizontal line 6. That's this right here. And we're going to subtract the lower function, which is 2 root x, so minus 2 root x. So now it's just the same exact question as the first question in FRQ1, except the integration is going to be a little bit easier for this one. So that we end up with 6x minus, well, this is 2 times x to the 1/2. So we end up with 2, I'll write it like this, x to the 3 over 2 over 3 over 2. And let's just simplify this. So 6x minus 4 over 3, because we can multiply by the reciprocal of 3 over 2, x to the 3 over 2, evaluated from 0 to 9. Well, the 0 term doesn't matter because both these terms, if we plug in 0 for x, are going to be 0. So now it just comes down to plugging in 9. So we end up with 54, 6 times 9, minus 4/3 of 9 to the 3 over 2. Okay, and how in the world do we evaluate 9 to the 3 over 2? Well, 9 to the 3 over 2 is the same thing as the square root of 9 cubed. 9 can be written as 3 squared cubed, because 3 squared is equivalent to 9. So this becomes the square root of 3 to the 6, which becomes 3 to the 6 over 2 if we convert it from a radical to a fractional exponent. And then this becomes 3 cubed, which is equal to 27. So our answer here is going to be 54 minus 4/3 times 27. Well, one of the 3's in the 27 will cancel out with the 3 down here, so it becomes 54 minus 4 times 9, which is 36. And so we end up with 18 as our final answer for the first part of FRQ number 2. Letter B is going to look very similar to the last question in FRQ1. So imagine we have a dotted line up here at x equals 7, or y equals 7, sorry, because it's a horizontal line. Y equals 7. The volume generated by taking this region R and rotating it around the line y equals 7 will be pi times the integral from 0 to 9 of 7 minus the function that is further away from the axis of rotation. And in this case, that is going to be 2 root x squared minus 7 minus the function that is closer to the axis of rotation, which is 6. And so this integral expression right here, which we do not have to evaluate, is equivalent to the volume generated by taking the region R and rotating it around the line y equals 7. And you can simplify this if you want. You can change this over here to the number 1, but let's just leave it like that. Okay, and then lastly, we want to find the volume generated when we take cross sections perpendicular to the y-axis now, no longer the x-axis. So we're going to take cross sections perpendicular to the y-axis this way. And the height is 3 times the length of the base r. So if we want to find the area here, we need to find this distance, the base of one of these rectangles. And to do that, we're going to take this blue function, y equals 2 root x, and that gives you the height, but we want the kind of the width here. So what we're going to do is solve this for x. So y over 2 is equal to the square root of x, and so x is equal to y squared over 4. Well, if we know that that's going to be the base of each of these rectangles, if we know that the area can be found by taking the base times the height, and we know the height is 3 times the base, we're going to do y squared over 4 times 3 times y squared over 4. And so the area of this region we end up with is 3 times y to the 4th over 16. And then this is what we're going to evaluate or plug into our integrand when we are coming up with our integral expression. So the volume is equal to the integral from 0 to the y value of our point of intersection, which is no longer 9, it's the number 6, times 3y to the 4th over 16 dy. And this right here is an integral expression that gives you the volume when we have cross sections perpendicular to the y-axis where the height of the rectangle is 3 times the base of the rectangle. Okay? And then to wrap up this lesson today, I want you guys to work through FRQ number 3 here on the OneNote. And then if you have time, if you want more practice, work through FRQ number 4 as well. The answers for both of these questions with the mark schemes are in the OneNote.